Okay, so now we will learn our Ramsey theorem. So what is Ramsey theorem? So I just pulled out two rotary numbers. In Korea, so this is one of the rotary number. So this is like 2, 8, 28, 30, 37, 41. Another rotary number is 7, 11, 12, 21, 26, 35. So there are lots of conspiracy on this rotary number. People might say that this is not random. How can it be random? And those people have this conspiracy that they pre-design the number so that only selected number people can get it. And if you see it, you might see that okay, it is really random. For example, if you take these two numbers, summation is 30. Okay, sounds suspicious. And if you see it here, then what? This number, this number, this number is arithmetic progression. And if you check the rotary number, lots of them contain this kind of pattern. If this is truly random, why would it contain such a pattern? And that's one of the logic that those people who believe in conspiracy are false. Okay, why would this happen? Of course, this is psychology. As a human being, we see something, then we tend to find some pattern. Maybe you can say this is also biology. We are evolved in such a way that, always like save our mental energy, our brain power by finding some pattern and then just remember the pattern and don't remember the too much detail. That's how our brain works. And as a mathematician, we can actually see that we can actually show that this is not really weird phenomena. It is not really a likely event. You can just simply count the number. So this is out of 43 number, you choose 45. Yeah, 45 number, you choose 6 number from them. Then out of them, you count the number of tuples, which contains 3 numbers, which is solution of this equation x plus y equals z. And also you count the number of 6 tuples, which contain arithmetic progression of like 3. Then you will see that the proportion out of all this is not so small. So this is, not a likely event. Most of the rotary numbers actually have this kind of a pattern. So this kind of tells you that whenever there are some chaotic things, it is, certain well-organized pattern tends to appear even in this chaos. And sometimes it's not just tends to appear, sometimes it must appear. So in short, we can say that the order arise in chaos. So what's Ramsey theory? Ramsey theory is a mathematical attempt to show or study this phenomenon. So for that, we want to, study about this Ramsey theory. And for this, the spiral generalization of graph is useful. So we consider the concept which is called hypergraph. Hypergraph H is, again, just like graph, we consider a tuple which consists of a vertex set, say B of H, and on edge set B of H, such that each edge, sometimes it's called hyperedge or sometimes it's called edge. Let's not say each edge is a subset of vertices. For graph case, what was the edge set? If we just consider graph, not multigraph, graph case, all the edge set, all the edges are subset of vertices which have size exactly 2. For multigraph case, it was M 2. It's either loop or, edge of size 2. But here, we don't put such a size restriction. So this is the generalization of graph. And we said that it is are uniform if all edges have size R. So in other words, two uniform hypergraphs are the graph. And we say that some hypergraph is complete are uniform hypergraph. That's the hypergraph whose edge set consists of all subsets of size I. And we write R graph as a short of R uniform hypergraph. So graphs are two uniform hypergraph. And we said hypergraph is simple if there are no two edges E and E prime. Such that one is contained in the other. Simple two uniform hypergraph is a simple graph. So this for with the multiple edges. And for hypergraph generally we for with two pairs of the edges such that one is contained on the other. Okay, with this we will discuss about the Ramsey theory. The most simple explanation of the Ramsey theory, most simple example, simple and probably most famous example is about this. Is this. So also you have a K6. You have these edges. Maybe 6 vertices is too many, so let's not throw it. In case 6, we consider a red, blue coloring, the edge coloring. The edge coloring which does not have to be proper. So we have 6 vertices that are 15 edges in there, and we consider edge coloring using color either red or blue. Then what we want to show is that there must be a monochromatic triangle. How do you know it? You just click arbitrary vertex, then there are a certain number of edges here, 5 edges incident with it. By Pythagorean principle, we can already choose 3 of them with the same color. It could be, 4 of them are red and 1 blue, or even 5 of them are red. Or, there could be 3 blue one and then 2 red one, but always you can find the 3 of them with the same color. Then you see here, if one of the edges is red, then you find the red triangle. We are done. Otherwise, all of them are blue, and you have blue, blue, blue. You find the blue triangle. So this shows that this is true. On the other hand, if you have only 5 vertices, then you can color the edges with the 5, C5, and then blue C5. Then this doesn't give any monochromatic triangle. So this 6 is optimal in this statement. So this is an instance of Ramsey theory, and then we want to generalize for this for bigger number. Here you have triangle, then you get this number 6. What if we consider more bigger number? And we can, there are many ways to generalize it. That's one. And then another one is that we only use 2 colors here. What if we use more colors? And also we can consider a hypergraph instead of a graph. So we will define it this way. So K coloring is the function. Okay, before defining what Ramsey number is, let's define certain thing before. Okay, coloring is function that favors its domain element with one of K colors. So, then we use S should R to denote the family of R subsets of size R of the S. In other words, it's the same as a complete R uniform hypergraph on the vertex at S. Under coloring of the S choose R, if a set T is pi homogeneous, if its R subset or at the same color line. With this definition, now we define Ramsey number, which is number 6 in this specific case. So given number P1 to Pk, if there is certain n, natural number n, such that in every k coloring of the set of side n, say bracket n, and you consider all the R subset of it, and then you color it with one of the k color, and in every such a k coloring, if there is an I homogeneous set of as Pi for some I, so if this holds, that holds for this n, then the smallest such n is called the Ramsey number. And then we write as a R of P1 to Pk, and then you put the semicolon and then put R to denote its uniformity. It's about the R uniform hypergraph. Okay, with this definition, how can we summarize this phenomena here, this example here? So we consider the graph, and then we use two colors. So we have to put two numbers. And then we were looking for monochromatic triangle, so red triangle or blue triangle. So this. And then 6 was sufficient, but 5, we had an example that we could avoid the monochromatic red triangle or blue triangle. So 6 is the smallest such one. So this is what we done. Okay, so we define this. And of course, what we want to do is find the exact value of this. That would be great, but that's too difficult. We want to find some bound, upper bound and lower bound. That would be what we want to do. And before that, we have to start with showing that it exists. Maybe, this number might not exist. No matter what natural number you take here, maybe we can avoid I homogeneous set of size Pi for every I. Then we can find the K coloring. But something like this for any large n, then it might not exist, right? So but we can actually show that this number is well defined. It must exist. So for beginning, what happens if R is 1? Then what? Now your hypergraph is one uniform. And then you color. So it's same as coloring the vertices. You color the vertices and then you want to find the monochromatic set. Then what? This monochromatic set is just a set where every vertex has the same color in there. So this is a Peterson principle. It corresponds to Peterson principle. Then what do you know? It's P1 to Pk1 is same as the P1 minus P1 plus P2 minus 1 plus Pk minus 1 plus 1, which is P1 to Pk, you sum, and then subtract K minus. So basically what it says, if you have like P1 plus P2 minus 1 elements, then you color some of them red, and some of them blue. Somehow, yeah, blue, 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 blue. Then either there are P1 many red vertex or P2 many blue vertex. One of them must be there. Because otherwise you have less than P1 minus one, less and more P1 minus 1 red and most P2 minus 1 blue. And total number is smaller than what you have, or contradiction. So we know this value. Then now we want to show that for any R, this exist. So this kind of give us the base. And one more thing is that as we are mostly focusing on graph, if the last number is 2, meaning that if we are about graph, twin hypergraph, then we simply omit it. We omit it if it's 2. Okay. So now we prove the following Ramsey theorem. Ramsey show that given K, R, P1 to Pk, any natural number, the Ramsey number are P1 to Pk semicolon R dg. Okay. To simplify our proof, let's only consider where there are only 2 colors. And for bigger K, I mean, proof is essentially same, so you can convince yourself. So we use induction on R. And this is double induction. The proof of the induction step itself uses induction of the summation of Pi, the P1 plus P2. Okay. And for base case, R equal 1, it's okay, so that's general principle. And when R is bigger than 1, for this, I mean, this is the bigger outside induction base case. Then inside induction base case, if some Pi is smaller than R, then what? No matter, I mean, you just take any set of Pi objects, then it has no R subset. So, vacuously, every R subset of this is at the same color that belong to a class I. So it's colored with the color I. Hence, Ramsey number say PQR is minimum out of P and Q if one of them is smaller than. So this gives us the base case for the inside induction. So now my induction hypothesis, so think that this one is bigger than or equal to R. Let's just write P and Q instead of P1 and P2. So P is P1, Q is P2. By induction hypothesis, we know that the Ramsey number of P minus 1Q exists and Ramsey number PQ minus 1 exists and Ramsey number P prime, no, this is P prime, let's say this is Q prime, and Ramsey number of P prime, Q prime, R minus 1 also exists. Then we add 1 and then let capital N be the number. So these two exist because of the induction hypothesis on the inside. So this sum is more than P plus Q. So this exists and this exists. Then this one exists because of the induction of R. We assume that the R is smaller than, up to R from 1 to R minus 1. This Ramsey number always exists, no matter what P and Q are. So let's take S as the set of this capital N element. And we choose X from this. And we consider two coloring F of all side R subsets of this F. Now I want to show that in here we can find either one homogeneous set of size P or two homogeneous set of size Q. And that shows that this N satisfies this condition. So there is one natural number satisfies this condition, then naturally there is this smallest such integer. So this shows that the Ramsey number exists. Now what? We have this S and S. Then let S prime be the remaining one. I want to generalize before what we do. When we show that R33 is 6, we have this red, loop. Then we focus on here. And then we show that inside of here, you have either red triangle or blue triangle. I want to generalize it. But here, this was H. Now we are R uniform K. How do we do it? We use this coloring F to define or two coloring, say, F prime of I write one uniform complete graph on F prime. For each set A, which is size R minus 1, we let F prime of A be the color of this FA union with the X. So just like you take red, that's, you consider it as a red vertex and red vertex. And then here you consider blue vertex. Then what did you do here? You apply pigeonhole principle, and out of 5 vertices, there must be 3 red vertex. So that's what you did here, right? So similarly, now we want to apply Ramsey number on a smaller uniformity. So since it has prime, it's Ramsey number of P prime, Q prime, R minus 1, because what? N was it, negative 1 vertex, 1 is eaten up by this, taking vertex X, the remaining one. So because this much size, the induction hypothesis implies that S prime contains, say, either flat homogeneous set of size P prime or blue homogeneous set of size Q prime. Yeah. So when R equal 2, that just hypothesis is exactly the diffusion principle. Then what? By symmetry, assume that we have red homogeneous that of is P prime. Now what you have? If this red homogeneous set, meaning that no matter what I minus 1 vertex you take, if together they are forming red edges in the original coloring hand. So what do you know? And let's say this red homogeneous set is T. So since this T has size P prime, which is R of P minus 1, 2, R, within this T, there is Pn minus 1 that is not homogeneous under this coloring F, or a Q set that is blue homogeneous. Under F. If the latter holds, we are done because we find the blue homogeneous set of size Q as it meets. If the former statement holds, then there is its finite one set, say P, which is not homogeneous. Then we consider P together with X. Then what do we know? This is T, this is P. And every R set inside of here is red. Then every R set containing X, and then rest of them in P, is also red. From the definition of this T, I might one sets in P are all red under the F prime, meaning that so their union with F are also red under this F. Hence, we get that the P union with F is red homogeneous. Under F of size P. So this shows that this capital N is, satisfy this property so that this exists, this Ramsey number exists. Okay. And you can compute this N. From this proof, you can actually compute this N. In this induction, you just keep repeating this and then see what number you get here. Then you can actually get the upper bound on this Ramsey number. And just focusing on graph case, what you just show this inequality. Why? Because what? Once you have these two, and R is 2, here, what's this? This is simply P prime plus Q prime. So P prime plus Q prime. Because of this was just the P-general principle when R minus 1 is 1. And that's just the summation of these two numbers minus 1. And then you take the plus 1 and these two. So this shows that when R equals 2, this new Ramsey number, RPQ, is at most R of P minus 1 Q plus R of P Q minus 1. And that's why you have it here. Then as a corollary, you can show that the RPQ is at most P plus Q minus 2 should P minus 1. And proof is what? Again, use induction. And based on this previous theorem, you have this. Then assuming that this is at most P plus Q minus 3, which is induction hypothesis, and this is at most P plus Q minus 3 should P minus 2, which is the induction hypothesis, then you get that the bigger one to satisfy the induction hypothesis. So this completes the induction. So this shows that say when P and Q are same in particular, so this is called the diagonal Ramsey number because if you write the number 1, 1, 2, 2, 3, 3, 4, 4, and then write down the number of Ramsey numbers, so R and N are on the diagonal. So this is called the diagonal Ramsey number. This is the most P minus 2 should N minus 1, and in particular, this is more than 4 to be N. And best known upper bound is by Enkos, Griffith, Boris, Tastra, Gude. They very recently, in 2023, show that its number is at most 4 by some constant to the n, or some constant C bigger than 100. 1 over 200. And as I mentioned here, 2023, and this was breakthrough. This was exponential improvement from the previous bound. And previous best bound was 4 to the n minus real of n. Here, real of n is a function which grows much slower than n. So this is a function such that the limit n goes to infinity, fn over n is 0. Then we write such a function as real of n. And yeah, so because this number was proved in 1930s, this improvement was take almost 90 years. Okay, that's the best known upper bound that we know. We will also discuss about lower bound. And before we discuss lower bound, we will see one application of this Ramsey theory, and then that kind of justify you why this is important and why this is interesting. And I will do that in next video.